Testing sound. Indeed, that works. Well, that's good. All right. What are we working on today? Today, we are again back to working on the C++ module mapper. So, oh, I should. So I discovered a bug, and I had a bunch of code here that I then took out so that I could exercise the bug. Um, because the code fixed the bug. So we are going to double check something here. I bet this test will now fail. Indeed. What? Yep. Yep. Okay. Assert B bar equals. Yep. Yep. So basically, DB3's environment is the same as DB2's. Um, so let's push our so here's where the bug is, right here in the init method. There we go, the init method. This is the bug. It should be, stupid thing and its focus follows most doesn't work properly. Should be that. Now I bet it succeeds. That's a thing to do when you discover a bug. This one, I discovered the bug by inspection while I was working on the code. But that's what you do. When you discover a bug, you go and you write a test that will cause the bug to happen before you fix it. Because regression test, the bug might crop up again. In this particular case, for this particular bug, it's unlikely to crop up again. But, better to be safe than sorry. Better to have a test that will make sure that the bug never shows back up than to not and have the bug show back up later. All right, then. Now let's do all right. So the problem is that part of this change already is in here. So I'm just going to edit the change to remove the offending portion, the portion that's already there. Just like that. Let's see. Let's look again. What? What failed about this? This is perfectly reasonable. Yes. Why can't you apply this patch? Anyway, it's obvious enough what should happen. All of this stuff minus the pluses should go in. So we'll just take this, copy it, click here. like so. I don't know what its problem is here, what it expects. This should be just fine. Okay. What is the problem here? What does it not like? Oh, it's this indentation level that's the problem. And that indentation that level that's the problem. There, that should be correct. I'm pretty annoyed about this actually. There. So I added these put and get methods. Um, but they're not at all what's going to be happening. This is just a sort of a sample of what's to come. Um, Yeah. Yes, these are just a sample of what's to come. Um, and let's see, does PyTest still work? Yep. Okay. So, think. There are several different problems going on here, and I've kind of realized what these problems are. So, I want to ensure that two compilations can't happen at once. Now, the way the whole compilation tree works, that shouldn't be able to happen, but it's also possible that there's two compiles running at the same time. And so that might happen. It might happen. That problem is if there's two compiles running at the same time, there might be a deadlock situation where one starts before the other one does. That's an interesting question. So, like, they're both running at the same time. One of them starts compiling module A. Module A and module B both depend on top. One of them starts compiling module A and then realizes it needs to start compiling top. The other one, that's module B, then starts, I can't, but it can't continue. Okay, so that's fine. What happens when no, that's fine too. Okay, I'm trying to think of different scenarios here of possible problems that could happen. Um, so the entire dependency tree from child to parent is going to end up being sort of locked for compile until the parent finishes and then that child and that child and that child. So any other compilation that's continuing on, no matter where it is, unless it's changed the relationship somehow. But if it's part of a, yeah. One thing that would be really nice to do and can't be done is lock the file system while compile is happening. Because if you don't, all kinds of weird things can ensue. Oh, you edit the file while a compile is happening. While you edited a file, change the dependency tree so that uh, there's some combination of the old dependency tree and the new dependency tree, where if you squish them together in the right way, you end up with a cycle. And then that creates a deadlock situation where one of the two compiles might end up be waiting for each other forever. So that's one possible scenario. Both compiles should fail. The way to solve that is to have a timeout for a compile. Like if a compile takes longer than 5 minutes, but that's tricky. What timeout is long enough? It should be like almost, yeah. It almost has to check the system load. Go. If it doesn't look like there's any progress being made on a compile right now, and I'm waiting for a compile to finish, then clearly I'm deadlocked. That would be have to be how that would happen. Uh, so you're prevented from deadlocks normally if the files don't change while compiles are happening. No matter how many compiles happen at the same time, if the source files aren't changing while the compile is happening, then uh, all files are going to lock in a specific order where uh, at least one child will be locked before the parent gets locked. Um, and so another compile upon entering will basically be blocked at the point where it enters the dependency graph uh, at a spot that's currently being compiled. But that one can't be blocked over here because this can't be a yeah. You'd have to have a cycle in order for these two, but it's a DAG. It's a directed acyclic graph, and so there aren't any cycles, and so it should be fine. So I need some kind of locking mechanism to make sure that two compiles don't happen at the same time. So I'm asking ChatGPT some questions about LMDB. uh, because I'm trying to make sure that the behavior is exactly as I think so that I can make the locks work properly. I need to know that if I do Okay. So I do have a way to atomically lock these uh, these files as I'm compiling them, or lock the database entries, but also lock the files. Like I don't want to run two compiles in the same file at the same time, right? So yeah. Oh, this is kind of weird. Also, so it looks like the values that are stored in the database are going to have to be different from the values that get passed into the interface. Um, so, and that is going to be the compilation results. Okay. Now here we have a bunch of stuff. We have and then we have compile PID. So if compile PID isn't none, that means a compilation is currently in progress. What else do I need to track? Anything else other than that? Uh, uh, okay. Now we have one last thing that we need here. And now here, everywhere we have stat data, we need relevant stat data. So will this be or none? Yeah, we'll make this or none as well. No, no, this has to be there. There. That's better. But this means that the module value that shows up, like all this stuff, I'm going to have to modify this test really heavily to make it work again. So none, comma, true. There. That's the thing that I have to do here. I want to replace it. Hmm. You know what I'm going to do? I am going to pull up Emacs briefly. Um, and for that, I'm going to temporarily switch back to chatting mode because I want to do some stuff. Ah, uh, Sabina Hofsenfelder had a fun video earlier today. She talked about a physics paper positing that the structure of space-time is a quasi-crystal because everybody wants to quantize space-time somehow. Um, and if you quantize space-time, then space-time ends up being made out of something and it has a structure to it. And so then what is the structure? And there's all kinds of problems that you encounter if the structure happens to be a regular structure. There's certain things about relativity that just don't work right. And so, but turns out that if the structure is a quasi-crystal, then maybe those things can be made to work right. Maybe. Um, but if it's a quasi-crystal, like a Penrose tiling or something, then that means there's no straight lines, no such thing as a straight line. Um, and she said something about because the whole thing was about crystals, uh, and in the sense of regular ordered structures repeated through space. Um, she made a joke about aligning your chakras, and pointed out that it might not be possible to align my chakras if all this was true. So we are going to pop up Emacs. Emacs, I can get this job done, and I know how to get it done. Okay. All right. Back to programming. Mostly I was fiddling around with windows and stuff in a way that I did not want to do while I was on when my desktop was visible. That's why I switched back to chatting mode for a brief bit. You had to be to endure my full screen of my face. Ah, anyway, so Emacs, this is relatively trivial for me to do. Probably is trivial on the other editor. I just don't know well enough. So there. Hey, so there. That's been fixed. That's the input data, and the include test data is just the same because the include key hasn't changed. The include, yeah. And for this, I have to put in, oh, you know something? Since all of these are true, I can just do it a different way. So Emacs to the rescue again. And I was a little more careful about how I defined the macro this time. And so, yes. Yep, much better. Okay. So now for this, all I really have to do here, because I'm doing the same thing, I'll just do and then for the module, the BMI path, we'll just make it the same as the module path. There we go. All right. Now let's run PyTest and see what happens. It should mostly succeed. Well, it should fail, but the failure should be yes, that kind of a failure. Where a bunch of stuff is just not the same. So now we're going to get into Emacs again. And you know something? We're going to fix some of the problems here by just making the window a lot wider. Then I don't have to be so careful about how I define my macros. There we go. Put all this in register A. So now we do this. Yep. It's magic. Woohoo. Still failure. What failed this time? DB header key. I don't know how that got in there. Oh, I messed up the files slightly, but only slightly. There, much better. There we go. Fix the test. All right. I was just thinking through what I was going to do here. Whee. I just want to verify through meld, which is a fantastic diff tool, by the way, that in fact the changes that got made were the changes that I expected to be made. All kinds of BMI path added, the test output. Yep, exactly. Exactly. Okay. Uh, add results object. I don't know how that A got in there. Uh, Gotta scrap 10 characters. So 75 need to find a way to get rid of 8 more. That works. It's ugly. I don't like that exactly, but I couldn't think of a way to say what I wanted to say in a shorter way. Um, so there we go. Okay. I think I should make put and get be also private functions. It's not the right implementation, but we also need another class here, another data class. So what's this all thing about? So basically this is kind of an indication of what symbols within this module are considered public symbols, which ones you should be using for stuff. The real effect it has is if you do like from something import star, you only get the stuff that's in all when you do the import star. You don't get any other things from the module. You only get the things listed in star. So when you import star, you don't get just all kinds of stuff willy-nilly. You get only the stuff that's in there. This is not how this is supposed to work. So loop. So what I'm doing is I'm trying to think through what's going on here. So when a compile happens, I need to inform the dependency database that it has started. At which point it updates the thing with a there's one other thing that I absolutely must have. When I start a compile, I must know the there. So why do I want to do it this way? Let's see, this is still less than 80. Okay. So result equals. Exactly. So you know something? I don't need to know the PID because I'm the PID. I need to know the module path. That's all I need to know. Yep. Like this. Saying it's my PID is redundant. DB module value. And then what do we want for a module value? We want the PID false none module path none blah blah. Yep, that's exactly what we want here. And actually, we'll put in and this is exactly what we want. Transaction dot put serialized value turn compilation status start. All right. Serialized value. And I don't have to have the parentheses. All right. Silly thing. So, oh, hi there. So, what it does. So are you familiar with C++? How familiar are you with C++? Sorry, I was paying a whole lot of attention, and so I didn't notice you there. Do you know about a C++ feature called modules? Heard of it. So modules are kind of a replacement for include files. So I'll show you some examples here. I have this and for this thing for testing this, I have a test CPP project. So I'll show you it. So I have a source file, right? Main. Notice how I'm doing all these imports, right? No includes, just imports. That's because that's That's what modules, how you use modules. So import top. Now, if we look at modules here, we have top.cppm and so on and so forth. If we look at modules top.cppm, it has this thing at the top saying, hey, this is a module. You need to kind of do that before you do these includes to sort of signal to the compiler that, hey, there's modules here, and all the stuff you see here in the includes are part of the, are sort of symbols that are not going to appear in the module. Because in modules, one of the things you also have to do is explicitly export what symbols are part of the module. And so this export module top is saying, okay, now we're starting a module, and the module we're starting is named top. And module names can have dots in them. And so that's so you can have sort of a hierarchy. And then you say the symbols, the basically define the functions, the function declarations that are going to be exported. And these can be inline, like I could export inline blah and then have the function body here if I wanted to. Or I could just say, hey, I have a function named this, right? Very much like a header file. But if I don't export it, this symbol, this thing that I define here, is accessible from within the module, but it won't appear anywhere else. Nobody else will be able to see it. Only people who are inside the module, only other things that are in part of this module will be able to see it. And so it will basically be private. And then here I'm exporting a type. I'm saying I have a concept called numeric. I don't know if you know what concepts are, but they're kind of a way of constraining template values to have certain properties. And then I'm saying I have a template here and I have a type parameter that has to satisfy the numeric concept and named base. And this is basically an implementation of the power function as a const expr function. And also too, I have a second template argument sort of, but it's not mentioned here. This is kind of a weird way to do this, but I have a kind of a second template argument that must satisfy integral, which is the exponent, because it only handles integer exponents. And then I have all this stuff here that implements it. But this is part of the module, right? So they say, okay, I'm not quite sure what you're asking, but I'll continue on with my explanation, and maybe I'll answer the question that you have, and then I won't have to dig into what you said to try and figure out what exactly you meant. Okay, so this is basically kind of like a header file, but not really. You're defining a bunch of things that will then anybody who imports this module will then suddenly be able to see all of these symbols. Yes. So here's a different module that I have called middle A. Also too, none of the symbols that appear in concepts, type traits, or limits or anything will be part of the module at all. There also are things that are accessible, like I'm actually using all the type traits here, but nobody who imports the module will be able to use standard integral, for example, even though I used it in defining something within the module. And then middle A, I just export module middle A. I didn't have to start with the module declaration because I didn't do any includes here. So I didn't have to include the global module fragment to say that there's things that I'm including. And so here I'm just saying, this is another module named middle A, and then import top. Now, what's interesting is nobody who imports middle A will actually be able to see anything from top. This import of the module is local to here. But these functions here, I'm exporting this inline, right? And this stands for module middle A print something, right? So this is basically a version of print something for middle A. And all it calls is print something with middle A as the first argument. And so it's calling the print something from top it can see that. But if I just imported middle A somewhere, I wouldn't actually be able to see print something. I'd only be able to see middle A print something. Um, you know, MAPS. And then I have middle B. I wanted a diamond graph here. So middle B also imports top. And then I have a bottom, right? And bottom imports middle A and middle B, same rules. And then it just calls both of them with bottom as the second argument. Okay, so now let's look at the implementation files. Oh, sorry. So in source, I also have something called top impl. So main you got to see. So I'll do source top impl. So here, again, global module fragment, include this thing. Again, it's a sort of a thing to tell it, the C++ compiler, that I'm going to be using modules, but I'm also going to be including things, and just ignore everything from a module standpoint in between this and that. But keep in mind, there will be modules. And then I say, this is part of module top. So there's no export here. So this is basically, I'm telling it, this is an implementation file for module top. And then I implement, this is how print something works, right? And this is how print value works, and so on and so forth. Like there's a bunch of functions in here for printing things. And the reason why I did that is because now I can import top, and it will print things to standard out, but none of the things that do the import of top will have to include IOStream at all. They import top and they get all of the top symbols, and they can call these functions, and then these functions will call the appropriate IOStreams thing. So it's a way of insulating the rest of the program from IOStreams completely. And if we do it source main.cpp, right? Here I'm calling all the various functions from the modules that I imported. And that's it. Why would you want to do this? What's the advantage of modules? Partly import makes more sense. Like import, it looks more like modern languages, because I could have periods here, and then something could decide the period means slash, and so then you can go find the module in a file system someplace, just like Python does, right? And also the import, like, since the symbols have to be explicitly exported, it gives you a lot more control than a simple textual inclusion. And various other things. But one of the biggest things is that modules, in fact, kind of get compiled. They might not result in any code, but they still kind of get compiled. And when they get compiled, they produce an output file, right? They produce but the output file is what's called a binary module interface. So basically the compiler pre-chooses it, like pre-parses the module and pre-chooses it and generates a data structure describing the contents, the C++ contents of the module. And then it dumps that data structure into a file. And then previous imports, when they import it, they just inhale that data structure into compiler memory in a relatively direct way without any parsing. C++ things can be very complicated to parse because there's a lot of declarations, there's inline functions all over the place, there's templates being expanded, all kinds of stuff is happening. And so it can be pretty expensive to include something, because when you include something, basically it's a textual inclusion. And so you're basically parsing everything all over again. And so modules provide you a way to just pre-parse it and to have sort of a binary chewed thing. But that leads to a very weird situation in compilation. So are you aware of like CMake and make files and things like that in C++, in the C++ build chain? Okay, so C++, right? It's a compiled language. CPP files generate a header file. You know, in order to demonstrate what's going on here, why don't I just do this? What did I call it? pi-cpp-modmapper. There we go. And then we'll do -03. These are all the compilation flags. Right. This is annoying. Okay. Here, I'm in the middle of doing stuff, but what I'm going to do, this is kind of like a git stash, kind of. There we go. Huh. Oh, I see. I forgot one thing. Notice how that popped up a whole lot, right? Here. We're going to RM it, and then we're going to try this again. So PyCPP modmapper works as a wrapper around the compiler. And notice now there's now a GCM cache, and we have prototype. Don't worry about it. Why the prototype thing exists? I'll explain. Don't worry about it right now. But then we have all of our GCM files that contain that. For some reason or other, G++ decided these things are called binary module interfaces, and the file extension for them is going to be GCM. GNU compiled module. So anyway, these are all the modules, and you notice they didn't exist before, right? They're brand new, and they're not that big. Well, top is kind of big, but yeah, that's those are the pre-chewed modules. And as you can see, if you look at one, it'll just be gobbledygook, right? You can see, oh, there's you can see some of the names from there, like operator, and there's also integral constant and a bunch of other things that show up in here. Is integral, public, is floating point, like a bunch of the names that I use show up in here, but it's mostly gobbledygook. Now, we also have the build directory, which is where I put main.o. Also, it now has modules in it, right? The modules can generate .o files as well, which not going to worry about that exactly right now. That's not, yes, it's important, but not used currently by what I'm doing. But some other project that uses modules in a slightly different way, the resulting .o files might also be important. But for what I'm doing with this project, no, with this test CPP project. So are you familiar with what a .o file is? Like, have you done C++ before? Like maybe with Visual Studio, it would be a .obj file, but on Linux, they're .o files. And I will show you what's in one, just so you have an idea. So this is basically the assembly language disassembled. What's actually in there is this is the hex for what's in there. But this is the disassembly this is the assembly language instructions that are used to implement main. And I mean, it's kind of clear that it's a pretty darn simple program, right? Because if we look at the source, right, main.cpp doesn't do anything that complicated. So it's not too surprising that it's not this long. And it has like 1, 2, 3, 4, 5 function calls, 6 function calls, 7 function calls. So 1, 2, 3, 4, 5, 6. I don't know where the 7th function call is coming from. These two are inlined, so they aren't actually function calls. And also the compile time constants, and it's a const expr function. It was actually able. So here, if we actually look at what's in the main.o, right? That's what's in the main.o. But objdump allows me to print out portions of the main, what's in main.o, and make it human readable, like show what the assembly actually looks like. And so that's what I'm doing. That's what I'm doing right here. This is just to demonstrate that main.o contains stuff that's dependent on main, right? This is the compiler processes main.cpp and produces this object code that's designed for the CPU to execute directly. And so when you make a program, and actually I'm going to have to do something else too, because there's so I'm going to have to do right. So there's that .o file, and then there's so then I can do this. This is going to be ugly, but it'll work. This is basically finding a list of all the files that end in .o, and then right there, that's the program, right? And you can see that this has a clear relationship with main.cpp. So that's the whole process, right? I had to compile main, and I had to compile top impl, and then I had to go through a link step where I took all those .o files and squished them together and made a single executable out of them. And then I could execute, right? So there's a bunch of steps. Each of those steps takes time. And so this file depends on that file, right? If I change what's in top impl, I have to rerun this step to recreate that file. So, so there's when you're doing a build, there's a bunch of tools that exist for C++, that exist in general. They are general tools that can be used for a lot of different things. They're very general purpose tools. And the whole idea of the tool is to express a bunch of dependencies for stuff that you might want to create, and then give steps of how to create it. And the tool like checks, is the thing that you want to create there, is the stuff that you create it out of newer than what it is that you're the output. If the stuff that you like, if if this file is newer than that file, that means that this file has been changed since that file was created. And that means that file probably needs to be created again, because maybe it's going to be different, right? And so make and CMake and things like that are ways of expressing, saying top impl, build top impl.o is built from this other thing, and here's how to build it. And then make goes through and checks which ones exist, which ones are out of date, and runs only the steps that are necessary to update for the modifications that you make, instead of having to rerun all the steps all the time. Okay. So that's what make files are for. And that's what normally what a build tool is. And they're normally external to C++. Like C++ always had a set of inputs and a set of outputs. And you could always list, like some of the inputs wouldn't be obvious at the time, but you can get the compiler to tell you what all the inputs are, because the inputs also include all the files that were included, right? And so the compiler, as it's compiling, can go, I used all these include files to produce this output. So then you can record that. So then later on, you can check, have any of the include files changed as well, right? And so you could do that. And so you could keep the build tool completely outside the compiler. But modules introduce a weird thing. Like, you know, when compiling main.cpp the first time, when it did import top, there was no top.gcm file. The GCM cache directory didn't even exist, right? And so what's the compiler supposed to do? And so a solution was come up with for handling this. And I will remove the log file to give you an idea of what's going on. So then we'll do the main.cpp again. Right. Now let's look in the map and the log file. So in this log file, here's what my tool is doing. I'm running a subordinate GCC to, you know, compile main.cpp into main.o. And then I also add this extra flag, module mapper. These are file descriptors. Don't worry about it. This is basically a way for the compiler to communicate back to the tool that I'm writing. And so then this is the top level compile. These are all messages associated with the top level compile. And it's like creating a dependency database. And then it says this weird thing, got command bundle. So this is basically GCC telling my tool, hey, hi there. And my tool goes, oh, yes, hello. And you want the module repo. So, hey, yeah, I'm PyCpp mod mapper, and I have the module repo here in this gcm.cache/prototype. That's what it is. And then the GCC tells me, oh, I need to import module top. Could you tell me where to find it? And I need to import all these other modules too. I need to import all these modules. Please tell me where they are. And so then I get that, and I don't reply right away because I looked and there's no, the module isn't there, right? So I had to say, it was there, but this is the part of the tool that I'm working on right now. So right now my tool just acts like nothing's there, that it has to do all the steps all the time. So my tool is going for top. I don't have top. So I better compile it, right? And so it then starts another instance of GCC to do the compilation. And this time, you notice I have the top.o was an output, right? But also this other thing, the CPPM file, right? The module file is the input. And then I also do this thing to basically allow that thing to communicate back with my tool. And so then the compilation for top says, oh, yeah, hey, I'm GCC here. I'm trying to compile top, right? So that new GCC is also communicating back to my tool and saying, you know, I'm trying to compile this top thing, and I've got all these include files. Please tell me where to find them. And my response for include files is to just remember, oh, it needed this include file while it was doing the compilation, but also just to say, yeah, you found it. Go there and go get it. That's what that bool true is. And so then that's what all this is. And so basically, the reason why GCC wants to have a conversation with something is it needs to know where to find the modules or what to do if it can't find the module, right? Because you did this import, and the import might require GCC to compile something else. And so that's, and GCC can't know that ahead of time. It can only know that as it's processing the file. So as it's processing the file, you might need a tool that kind of brings the thing into existence that it needs. And so that's what my tool is. It's like sits there in the middle of the build process to handle all these module includes and communication with GCC to make sure that when GCC imports a module, that that module is up to date, and that it's been compiled. Does that make sense now where my tool is sitting? Okay, that's good. So that's the goal of my tool. That's what my tool is about. Now, what I'm doing here is I'm adding this stuff to keep track of whether things are out of date or not. And so that's what this whole dependency DB is all about, right? This is the class that I'm working on. And in this dependency DB, I have to take into account the fact that there might be multiple compilations going on at once. Like one of the things that make tools do is make tools will frequently try to compile several things at the same time. Because the make tool goes, well, you have several CPUs, so why don't I just compile all the stuff all at once, right? Because each compiler can only use one CPU, so or one core, so I might as well start as many compilation processes as you have cores. So I have to take into account that, oh, lots of things might be trying to compile stuff all at the same time. So part of what I'm doing here is, okay, so I'm going to be keeping, oh, that's right, I have to Q push to get the code back. There. All right, there. That's why I couldn't find it. It wasn't there. Um, right, I have to keep track in my database. Oh, this thing, somebody else is compiling it right now. So whenever I start compiling something, I have to put something in the database going, hey, I've started to compile it. But also, I should check the database and go ask the database, hey, is something compiling this right now? And if it's something is compiling it right now, I should wait for it to finish. But if it isn't compiling it right now, then I can I can compile it myself. I can be like, yeah, all right, I'll start it. And so that's kind of what this is about, right? And then the other thing is there's some kind of elaborate stuff I'm doing with threads here because I'm using Python and I'm using async Python so that I can have sort of pseudo threads of stuff that's happening all at once. Because like I have all these compilations, right? And all of those compilations, all those instances of GCC, they're all communicating with the same program, the same process. So I have to manage communications with all these different GCCs that are all running at the same time. And so I'm using Python's async to do that. But the database transactions themselves might block on IO or things. And so one way to handle that is to actually have a bunch of threads for that do all the database stuff. And so then those threads will, block or not. But I need to have that interface back with the async stuff. And so that's what this stuff is about. Like start compilation sync is actually being run by a thread. But then the thing that the program calls is start compilation. And so start compilation just does what start compilation, it just returns the result from start compilation sync. But the way this works is it puts it on a little queue that gets sent to a thread thingy that then schedules it on a thread. And then when that thread has completed it, it sends it back to the async thing going, hey, it's done now. And then the async thing continues on. But the start compilation sync itself I have to be pretty careful. I have to say, okay, what module am I about to start the compilation on? Where, and also to the file path. I'm curious, I should probably say something about that. And then I start a database transaction and I turn the key, and like the key is in Python data structure, I have to serialize it into some bytes because the key value store doesn't know anything about Python. It says, oh, if you look up this set of bytes, you get that set of bytes, right? All the values are bunches of bytes. So I have to take the key and turn it into a bunch of bytes. And then I have to say, okay, does the database have this? And then if the database doesn't have it, then it's like, oh, well, this is a brand new module I've never compiled before. Or at least it isn't in my database. And so then I create a new database record for it. Otherwise, I deserialize what I got out of the database, and if the if the thing had a compilation PID already and it was my PID, that means there's an include cycle, like module bottom included module top, which included module bottom. So I was in the middle of compiling module bottom, and then I had to start compiling module top. And then while I was compiling module top, I had to start compiling module bottom. And I can't do that because I'm already in the middle of compiling module bottom. So I have to check for whether there's a cycle. If there's a cycle, that's actually a compilation error. You can't have cycles in include imports. But then but if the PID is not my PID and there is a PID, that means somebody else is doing it. And so the compile is currently blocked. Otherwise, it's like, oh, well, I can continue. So I update the value to say, hey, the PID that's doing the compilation is me. And the compilation is currently not successful. And the module path for the compilation is this here, right? And then I put that back in the database. So I update the database with this new thing, and then I return the result. And if the compile is blocked, I should actually have here that. I should be saying what PID is blocked in. Because I'm saying here that this returns compilation status in a PID. And so here's start compilation. It's a context manager, so I can use Python with. Python's with is a way of doing C++'s resource acquisition as initialization. And here, do yield result. And that's also dash greater than compilation status, comma, tuple. Python, you don't have to specify types, but if you do specify types, tools like this one can do a pretty good job of telling you stuff about what's happening. Like here, it knows result is this thingy, and yes, it knows already that result is going to be this because it can look at this thing and go, oh, this is going to return to that. And so, yeah. And here, actually, it shouldn't be PID, it should be int. And here it should be int. There, that's better. Why does it not like this? Well, this is very interesting, and I'm not quite sure what I'm supposed to do with this. Because I'm supposed to get something out of await. Like, this shouldn't be an async generator like await. I'm not understanding what's going on with this. But all these are right now. Yep. But this is not right. And so what's going wrong here? No. I'm not understanding what's happening here. I also have a thing to do in like 2 minutes that I should stop streaming for. Uh, I hope that you left wiser than you did. And I'm probably going to sit down and figure out what the heck is going on with this offline because I really want to. I I haven't ever used something like this before, and so I don't. My primary language, I very rarely mix async and threads in Python. In fact, I've never done it before. Oh, sorry. Um, I'm about to head out because I have something I have to do, or well, a meeting with friends in a couple minutes. Um, and so I hope that you learned something. Um, I'm having difficulty right now because the type of result is not what I'm expecting it to be. I'm expecting it to be uh, uh, this tuple type here, but it isn't. It's a async generator, and that's not what I'm expecting. So I don't know what's going on here, and I need to understand. And the reason I don't know right off the top of my head what's happening is because this is the first time I've ever tried to mix threads and and async stuff in Python. And I don't do async Python very often anyway. Python for me is usually a tool to write fairly straightforward utilities that don't need to do the async. Oh, I need to do several things at once or pretend to do several things at once type stuff. So yeah. Anyway, um, I hope that you have a good rest of your evening, and I hope to see you again on stream. I will try to stream again maybe on Thursday, but I often forget to do it or have something else that comes up. But it'll probably be less than a week before I stream again. Thursday, Saturday, Sunday, one of those days. By then, I will have solved this problem.